Afternoon to one and all present here, GATE aspirants. Greetings from Department of Civil Engineering, Vidyavardhaka College of Engineering, Mysuru. Welcome you all for a session 2, day 3. Right? Today, the session 2 is on structural analysis by Professor Kanmani S S. She has done her BE Civil Engineering from PES Mandya and MTech from SIT Tumkur. She is working as an assistant professor from past 8 years in Department of Civil Engineering in Vidyavardhaka College of Engineering, Mysuru. And today's session will be on structural analysis. I will hand over this session to Professor Kanmani S S. Over to you, ma'am.
Thank you, Abhilash sir. Thank you for the brief introduction, and I thank all the organizing committee members and the coordinator and HOD for giving me an opportunity to present here. So without a further ado, let me start this presentation. So in the last session on day 1, session 2, I was doing something on engineering mechanics. I was explaining about engineering mechanics. Today, it's time for structural analysis, which is the continuation of course, strength of materials. Engineering mechanics, by keeping the base as engineering mechanics and continuing this. In the last session, I stopped at analysis of truss, where I gave certain hints to solve the trusses by using method of joints and method of sections. Now in this session, I'm giving a presentation outline as we are going to study analysis of trusses in deep, wherein I'm going to give a brief introduction. We are going to study about what is zero force members again, method of joints, method of sections, and we are going to find the deflection of truss joints, and then redundant trusses, which are nothing but indeterminate trusses. And we are going to solve few exercise questions and we will explain it. And on the other hand, I'm going to continue with the analysis of three-hinged arch. Of course, we have to continue with the cables. In the next session, I'm going to take up with the cables and ILD. Afterwards, we'll summarize the presentation. To start with, analysis of trusses, the assumptions, which I already told in the last session 2. When the assumption of trusses is like this, members are connected at its end only. It will not be connected in between the members, and then all are joined by frictionless pins, nothing but hinge supports are provided. And loads are applied only at the joints, even though if you have a number of loads, it may be a load like a wind load or any other load, then it will we assume it to be acting only at the joints. Okay, maybe a UDL or it may be a UEL. We'll convert it to a single point load. We will apply that only in the joints. Maybe a wind force or any lateral force, we will apply only in the joints, and the self weight of the members are neglected. These are the basic assumptions of analysis of trusses, which makes it simple to analyze the trusses. Coming to this, basically what is determinacy and indeterminacy of truss. Basically, we have two different types of trusses, perfect truss and imperfect truss. A perfect truss is something like, it is called as a determinate, stable determinate truss, wherein number of members are equal to 2j minus r, where j is the number of joints and r is the number of equations of equilibrium available. I explained you this in the day 1 session 2 in detail. Moving on to imperfect truss, this is one where number of members, nothing but unknown members in the truss, are not equal to the available equations of equilibrium, that is 2j minus r. If so, we have two cases. If it is greater than number of unknown forces, if the equations of equilibrium are less than the members, or I can say if the number of unknown members or number of unknowns in the truss are greater than the available equations of equilibrium, we call it as redundant trusses. Redundant trusses are nothing but indeterminate trusses. On the other hand, if the number of unknowns are less than equations of equilibrium, we call it as a deficient truss. As I told you, it is an unstable truss. So now moving on, I have taken few examples of degree of indeterminacy. The first one, it is a simple truss where we have the number of members. If you see 1, 2, 3, I'll go with the in the clockwise direction 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So totally we have 13 members. Out of this 13, if you see the joints are 1, 2, 3, 4, 5, 6, 7, 8. So 8 joints are there. If I consider the whole structure for external indeterminacy, then we have 3 equations of equilibrium. So 8 joints, 13 members, 3 equations of equilibrium. So what is the solution? Here we have 13 members and 8 joints. The degree of indeterminacy has the formula goes the unknown numbers, unknown forces in the members, it is 13, minus available equations of equilibrium are 2j plus 3 is the equations of equilibrium. So degree of internal indeterminacy is 0. If you see external indeterminacy, the available reactions, support reactions, here we have a hinge and a roller, totally 2 plus 1, 3 reactions minus 3 equations of equilibrium. So it is externally stable and determinate structure. So this is how we find the degree of indeterminacy. Taking another example, if such question is asked, then you can just calculate the number of members. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 members, nothing but 9 unknown forces. And the reactions, and the joints, if you see 1, 2, 3, 4, 5, 6 joints. So 6 joints, 9 members, and 3 equations of equilibrium. To solve this, we will get like this. So 9 is the number of members, 6 is the number of joints, into 2. You know what is this 2? I told you in the last session itself. 2 is nothing but the equations of equilibrium available at each joint. So 2 into 6 is 12 plus 3. Then here plus 9 is that, totally 12 minus 12 is 0. So internally it is a determinate structure. Again, externally, totally we have 3 reactions and 3 equations of equilibrium. So it is externally also determinate. So it is a determinate structure. So if you want degree of indeterminacy, it is nothing internal indeterminacy. We will add it and we will put it up. Final degree of indeterminacy is found. Moving on to the problem number 3. Find the degree of indeterminacy for this structure. It looks like a previous problem only, but 2 more sections are added. Let me start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So totally 11 member forces are there, 11 unknown member forces. Joints are still the same 6 joints. And the available equations of equilibrium are 3. So it will become 11 minus 2 into 6 plus 3. So 14 minus 12 is 2. And it is statically, internally indeterminate. It is a redundant member. It is a redundant truss, we say. So degree of external indeterminacy, if you see, it is 3 reactions minus 3 equations of equilibrium. So it is 0. So total indeterminacy is internal indeterminacy plus external indeterminacy, which is works out to be 2. So it is a redundant truss. Next topic is zero member force. About this also a brief introduction is already given in the last session. Continuing that, we have A, B, C, D, in which we have one single joint, that is B, and 3 member forces. All these 3 member forces, if you observe this figure, force in member AB is collinear with force in member BC. These 2 are collinear members which are in the same line. Hence, the force in the third member will be 0. This is the zero force member concept. So if you find such members given 0, so this collinearity may be in any direction. If 2 forces are collinear to each other, then the force in the other member will be equal to 0. So another case is case 2, where you have at joint F only 2 forces. If 2 forces are there, 2 members are joined at one single joint, which are 90 degrees to each other, then force in each member will be 0. Force in each member will be 0. For example, if I have 4 forces at one joint, all are 90 degrees to each other, then you can straight away write force in one member, that is collinear members. Force in 2 collinear members are equal and opposite, equal in magnitude and opposite in direction. You can put it for 4 forces acting at one joint. So giving some example for analysis of such trusses, if you see this, a truss in which if I take this member, if I take joint G, If I take joint G, see this joint G, we have three members in joint G, out of which AG and GF are collinear to each other. They are in same line. They are collinear to each other. Since they are collinear to each other, the other member, whatever is connected to those two collinear members at joint G, it may be at whatever angle, the force in that member will be equal to 0. So I have applied that directly without solving. Once it becomes 0, I'll come to joint B. In joint B, leaving this, it is already 0. In joint B, you have AB one force, BC another force, BF is another force, wherein AB and BC are collinear to each other. Hence, the force in member BF is 0. Force in member BF is 0. Hope I'm clear. I'm moving to joint E. At joint E also, just like G, we have three members out of which two are collinear. So force in ED will be straight away transferred to FE, whereas the other member which is having any inclination at joint G other than this collinear member will become 0. Now moving on to joint C. At joint C we have BC and CD which are collinear, hence the force in member CF will become 0. This is how we find the zero force member. So if you find such figures, then you can put, well, so you should have the trick, you should know these two concepts. So if you know this concept, you can directly find out what is the member force. So now moving on, analysis of trusses again. I have taken one more example, wherein if you see this, I will start from joint B or joint D or joint F or joint H. In all these four joints, the case is simple. We have three forces or three members, wherein two members are collinear, the third member will become 0. So again, in all these four joints, B, D, F, H, since we have two collinear forces, the other member will take 0 force. Again, I'll move on to joint N now, where in joint N, leaving this NB force, we have three members, out of which two are collinear, hence the third one is 0. The same thing happens in Q, P, and J also, wherein two members are collinear, the third member will become 0. So once all these 4 plus 4, 8 members are 0, if you come to joint C and joint G, where you have two collinear members, BC and CD, here at joint G, FG and GH, wherein the other third force we have is MC, where MC will become 0. At this joint, KG is the third force, it will become 0. So this is how we will analyze or we will find the 0 forces. So moving on, after knowing this basic concepts, we will move on to the analysis of trusses. Truss analysis is done by 4 different methods, 4 different things we may be knowing. The first one is to understand or to know the member forces, especially in determinate structures. When we have determinate structure, we have 2 different methods to solve. One is method of joints, another one is method of sections. So when you have method of joints, the name itself indicates it, wherein we are going to solve or we are going to apply the equations of equilibrium at each joint. When method of section is something where you are asked to find any 2 or 3 unknown forces. You can take at that time. You can take method of section to solve such problems. Now moving on. Apart from these member forces in the determinate structure, they may also ask deflection of truss joints. So we are going to find out the deflection of truss joints either by Maxwell method, or we can also say it as a unit load method. By applying a unit load method, we are going to find deflection at the truss joints. It may be horizontal or vertical. It depends on the unit load. If they have asked horizontal deflection, we are going to take a horizontal force, your horizontal unit force. If they have asked vertical deflection, we are going to take vertical unit load. Indicating redundant means indeterminate trusses. So to find the indeterminate member forces, to find the redundant member forces of a truss, we are going to apply redundant trusses procedure, wherein we are going to apply minimum strain energy principle to find out the redundancy or to find the member forces in the entire indeterminate truss members. Now let me take the first one, analysis of truss by method of joints. I have taken one problem here wherein In the exam, they will ask you to find the member forces in A, B, C. They have given the names as A, B, C. So A, B, C members, only in A, B, C members, we have to find what is the force. So let us find what is the force. Before moving on, the dimensions, if you see here, the dimensions are like this. We have L, L, and here L. By applying similar triangle principles, we will get DE dimension as L by 2. We have an external load applied at P. We have a hinge at A. We have roller at D. So if I resolve and find the reactions at hinge, we will get 2 reactions, and at roller will get 1 reaction. So after this, we have to find A, C, B. Just look into the figure carefully. They said A, B, C. I'll take this force B first. If you see this RD, we will find the reactions here at joint D. If you see at joint D, I'm taking joint D. RD, if it is moving upward, since RD is collinear to DC or CD, the force RD is directly transferred to DC, and the third member will become 0. This is zero member concept. So the first thing is to find the reaction RD. Once we find reaction, we will say ED member or force in C is 0, and force in B is straight away transferred from RD. And if I come to joint B, wherein I need A, force A, joint B has 2 sets of collinear member, nothing but 4 members joined at joint B, where force P is collinear with BE and force AB is collinear with BC. Since both are collinear, 2 sets are collinear, when 2 set of collinear forces are joining at each point, at one point, then what happens? The forces in the collinear members are transferred to the other member. So straight away, the force P is straight away transferred to BE member. Nothing but A is found straight away. A is having the force of P. So P is moving downward. If P is moving downward, then here A will be in the upward direction. The force which is moving towards the joint is called compressive force. So force moving towards the joint is called compressive force. The magnitude of force is P, and it is a compressive force at joint A. At joint C, the force is 0. So the next last thing we need to know is RD. So let us write the equations of equilibrium. We will apply and we will get the final answer. So applying equations of equilibrium, sigma MA equal to 0, treating clockwise moment as positive at this joint. The first force we will get is, I'll take P in first force at joint A. This is force P moving like this in the clockwise direction. Force P is moving like this about point A in the clockwise direction. So plus P into distance is L. The other force I have is RD. About point A, RD is moving like this in the anti-clockwise direction. Since it is anti-clockwise, I'll put minus RD into distance from point A is 2L. Therefore, RD is equals to P by 2. We will get P into L minus RD into 2L. So LL goes, RD is equals to P by 2. If you apply summation Fx equal to 0, the only horizontal force we have is HA, which will directly become equal to 0. If we apply sigma Fy equal to 0, this is P, which is moving downward, minus P plus RA plus RD is equals to 0. Therefore, RA is equals to P minus RD. RD is nothing but P by 2. Therefore, RA will become P by 2. So this is finding the support reaction of the truss. This is the first step. The second step is taking each joint. We have to choose a joint where we have only 2 unknowns. So as I already told you, since our intention is to find A, B, C, read the question. You have very less time while tackling it, such problems in the GATE exam. Of course, these types of problems in structural analysis, from structural analysis side, they may ask 2 to 3, maximum 2 to 3 2 marks questions, and 1 to 2 1 mark question they may ask in the GATE. So you don't have much time to solve. So just read the question. They want us to find ABC. So we have to choose a joint where ABC is connected at the same time. The joint should have only two unknowns. So I'll start from joint D. At joint D, I have three forces, see RD, force in the member FCD, force in the member FED. I'll apply one first equation, sigma Fx equal to 0. So FED I have considered is as tension. Tension means force moving away from the joint is considered as tension. So I have considered all the forces as tension. So FED will become 0. If I apply sigma Fy equal to 0, RD is equals to, so plus RD plus FCD equal to 0, or RD is equals to minus FCD. So RD is nothing but P by 2. So FCD is minus P by 2. That is our compression force. Compression force is written as, written as a symbol. It is the force which is moving towards the joint. So this is the step 2 at which where we have applied a free body diagram at joint D. Now we are moving on to joint B. So we got force in member B and C. BC we got. Now I have to go with A. So to find A, I'm going to take joint B. To find joint B here, the main thing we should know is the dimension of this. So to find the dimension, I have plotted this again. This is not required since it is straight away, it is transferring from that point to this point. It is a waste of time to do this. Still, I have shown you if you want to find the member forces in all the members, you need this. But if you want only at A joint, then we are straight away going to put the free body diagram of joint B, where force in member FP is straight away transferred to FB. Okay, minus P minus FB equal to 0. Therefore, FB is equals to minus P. If you ask why you have not taken these inclined forces, we have to resolve these forces and then we have to take, if you feel that, remember it is a small tip to you people. If two forces are collinear, then from this figure, I can tell that FBC is equal to FAB. And these two are collinear, P is equals to FBE, but the thing is it will be in the opposite direction. Magnitudes will be same, directions will be different. If you want to solve this problem, solve by resolving these two, then also you'll get the same problem. Sorry, same answer. Moving on to the second problem, this is the problem asked. The force in the member DE of the truss shown in figure is, this is the member, this is the truss we have. So once they said D, what we usually do is we go to joint D and we will search how many forces are there. At joint D, we have 1, 2, 3, 4, 5. So we have 5 different forces. We assume that we have to solve this problem by finding the reactions and then by applying it to the each joint. But we have another interesting thing. That's why I always insist to people to read the question type twice. So they said the members, find the force in the member DE. So DE member has two joints, D and E. If D is having a number of forces, then go to E. At E, you have only 3 forces joining at the point wherein AE and EB are collinear to each other. Once they are collinear, the third member will be 0. So in this ABCD, we have to choose B, wherein force in member D is equals to 0. As simple as that. Read the question twice. The answer will be very simple. Read it twice. Moving on, problem number 1.3. They said the horizontal reaction of the joint E of the given trusses. This is the truss we have. So they gave one hinge and one roller support, and there is a load acting at joint C. They want us to find this HE. Finding HE is very simple. We are applying equations of equilibrium externally. Taking moment about A is equals to 0. We want HE, so I'll take about A is equals to 0. So I'll get this is a anti-clockwise moment. So minus HE into distance is 2 meter. HE into 2 plus 40 is moving in the clockwise direction. 40 is moving in the clockwise direction. And they have given 30 degree. They have not mentioned anything about this distance. So I'll consider this whole triangle and I'll find this distance. Tan theta is equals to 2 divided, that is adjacent side by opposite side by adjacent side. So opposite side is 2, adjacent side is x. So x found to be 3.46. So if I take moment about A, it is minus HE into 2 and then plus 40 into 3.46. So if you do that, you will get HE value. So HU value you will get in calculator 69.28, but the answers, if you see, you have √3, √2 times. So if you divide 69.28 divided by √3, you will get 40. So we can put 40 into √3 is equals to 69.28 kilonewtons. So the answer is D. For such problems, think twice and do it. Now moving on. Analysis of trusses by the method of sections. So use this method only when they ask you 1 or 2 members or 3 members. Okay. So what's the step here? We are going to cut the truss into 2 portions by using section XX. XX may be of any shape. You put straight line, you put curved line, nothing will happen. It is a section which cuts the entire structure into 2 parts. May not be equal parts, may or may not be an equal part. So you have divided into 2 different parts along this section. Afterwards, use the equations of equilibrium for the whole structure, nothing but for the part of this structure, that is summation fx equal to 0, summation fy, and summation mz is equals to 0. Apply this to one set or one part, then you will find the final answers. So before doing all these things, do remember that we have to find the support reactions. So see, along this red line, if I divide the section, if I want the unknowns Hg and Hc, if I divide this along this section, then the section will be divided like this, where I have mentioned it as F1, F2, F3, F1, F2, F3. We will divide this. We will get left hand side and right hand side portions. We can take any portions. Either you go with left or right, you will get the same answer because the system is under equilibrium. Now moving, I'm taking a problem, determine the forces in the members A and B. In the members A and B. A, B and C for the truss shown in figure. For the truss shown in figure. So I have made it, I have marked here A, B, C. I have 3 members in such a way that if I cut this section, it will not pass through these 3 members. So if that is the case, what we have to do, we have to solve this twice or thrice. So the thing is, if they ask 1 member here, 1 here, 1 here, then you have ultimately you have to put 3 sections. This is a quite tricky question. Of course, when this type of question is asked in the gate, you have to think before starting the problem. So I have cutted this here where it is cutting section B and C. If you come to section A, I'm very happy that section A is here, or the member A is here, where one of the joint of member A is connected to 2 collinear members. There are 2 collinear members and A is a third member. So I can put straight away A is a 0 member force. A is a 0 member force. Now I have to analyze only C and B. I'll cut at this point. And I will take left hand side before doing or before cutting this section. What I should do, I should apply equations of equilibrium. Now I have applied equations of equilibrium. Here we go. If I apply sigma fx equal to 0, if I apply sigma fx equal to 0, now what happens? Plus hp plus 5 equal to 0. Hp is equals to minus 5, nothing but whatever assumed direction is there, reaction direction, I should reverse this. So I have reversed here, Hp is equals to 5 kilonewton to the left hand side. Afterwards, I want a RQ. To find RQ, I will take moment about P is equals to 0. If so, see this 5 into 3, which is clockwise. So plus 5 into 3, plus 10 into 6, plus 10 into 9. See, all these are moving in the clockwise direction about point P. This is point P. This is plus 10 into 12. Again, this plus 5 into 15. And see this RQ about point P, RQ is moving like this. So minus RQ into 18. These are the vertical forces I have taken. Now the horizontal force left about point P, horizontal force is moving like this. So again in the clockwise direction, plus 5 into the height is again 3 meter. 3 meter is the height. So if you calculate that, so you can see this equation here, you will get RQ as 20.833. So if you practice you can directly do it without writing anything. You can straight away solve the problem by using a calculator, the virtual calculator, which will be provided for you in the final exam. And if you take sigma Fy is equals to 0, upward forces are positive. That's the sign convention I have taken. Plus Rp plus Rq minus 5 minus 10 minus 10 minus 10 minus 5. So is equals to 0, where in Rp we will get 19.166 kilonewton. This is how we solve to find the support reactions. Of course, I'm moving a bit faster because to solve this whole concept, whatever I have taken, is really very difficult to cover it within 1.5 hours. We usually solve such problems by taking 2 hours in class, but we cannot do such thing in the gate, or as all of you have already studied. I'm moving a bit faster. If you want me to repeat, just go back in the YouTube streaming and get a repeated telecast so that you will get to understand how I have arrived at this equation. So I have solved it and I have uploaded it. I have not skipped any steps. So step 2 is cut the section. Now I have to cut the section and I will consider only left side of the section. So considering the left side of the section, if you see here we have a 10 kilonewton force, and this is force FC. This is force FB, and I'll consider this as joint X. This has joint X, and I'll consider this as FX force. That force is not required. This force is not interested. We don't need that force since it is a horizontal force also. So what I do is, this is what we say a smart thinking. You have to think smartly. I'll take joint X so that I'll get FC directly. At joint X, if you take moment, the two forces, moment due to two forces will become 0. So if you take that, it will become, if you see this about this point, if I take, so first force is 5 kilonewton, which is in the same line. So due to this, we will not get any kind of moment. So 5 into 0, it will happen. The other force is 19.6 about X. It is moving like this, the clockwise direction. So plus 19.166 into the distance is 3 plus 3, 6 meters. Plus the other horizontal force, next force we have is this horizontal force. It is also moving in the clockwise direction. So plus 5 into distance is 3. About the same point, this vertical force is moving like this in the anti-clockwise direction. So it is again minus 5 into 3. And this 10 kilonewton is in the same line. So you will not get any horizontal, or we can say perpendicular distance between the two reference points. And then we have FC. FC is moving like this in the clockwise direction. So plus FC into the distance is 3 meters. So we'll get FC into 3. With that, FC is equals to minus 38.33. We have assumed FC to be a tensile force. Now, since we get minus, we will change the direction and we say that FC is a compressive force. Now what we do is, we will apply again at joint. So now I am left with two more forces, two more equations, that is sigma Fx equal to 0 and sigma Fy equal to 0. See this again, I told you, you need a smart way to understand, smart way to know it. You have Fx, which is an unknown force. If I apply sigma Fx equal to 0, this horizontal force will come into picture and it will make the life horrible and it will kill the time. So what we do is straight away take sigma Fy equal to 0. So if you take sigma Fy equal to 0, you will not get Fc or Fx. Straight away, you will get Fb and all other external forces. So I'll take sigma Fy equal to 0, Fb. So for Fb, if the angle is this, the vertical component will be here. The vertical component is opposite to the angle. Hence, it is a sine component, which is moving upward. Sine component moving upward. So I'll take plus Fb sine 45 minus 10 minus 5 plus 19.166 equal to 0. Therefore, Fb is equals to minus 5.89 kilonewton. Minus indicates that your Fb is compressive force, not the tensile force. So with that, I'll get C and B forces. Of course, force in member A is 0. So now moving on, after this method of section, now I'm moving on to analysis of trusses, deflection of trusses. So we are analyzing to find the deflection of trusses. So member forces in the determinate structure is over. Now the deflection. Now why this deflection occurs in trusses? There are a number of reasons, to jot out few. So the deflection may be due to external loading, or the deflection may be due to temperature changes. Of course, when there is a temperature effect, when there is a change in temperature, it affects the entire configuration of the trusses. And then there may be chances of improper connection with the joint because of manual error or lack of skilled labor, lack of skilled supervision. So these are the different reasons for causing or getting deflection at the truss joints. Now I have taken one small example to show you that. Say, for example, if you have a truss like this where the load is W1 and W2, if they have asked deflection at joint C, then what we are doing, the analysis is very simple. We are going to put the loads W1, W2, and we are going to find what is the member forces. We call it as forces due to external loads, that is P forces, we say. And afterwards, since the deflection is asked at C, we will remove all the external forces and we will apply deflection, unit load at joint C like this. A unit load, one is a unit load that is applied at joint C. After applying this unit load, we have to find the forces again in each member. Now you have to apply method of joints, which we already studied. So applying method of joints, we are going to find the force in each member. So if you consider this case at joint B, we have three members, out of which B joint is having AB and BC is collinear to each other. So at joint B, BE member is 0 but in this case, when we have external load exactly at joint B, then we can say this, since in all force members, two members are collinear, the forces are directly transferable. So force in AB is equals to BC, force in W1 is equals to BE in this case. So these are the simple tricks that will make you write or get the solution fastly. So after finding P forces and K forces, then we have the formula. So the procedure is to find the support reactions first and then find the P forces. Afterwards, remove the external loads and apply unit load at the required joint. So you need deflection at C, you're applying unit load at C. And then find the member forces and the support reactions due to this unit load, where you're going to get K system forces. Afterwards, we have a formula. Straight away, you should remember this formula. This is the deflection formula at the joint, where deflection delta C is equals to summation PKL divided by AE, where P is the member forces we got at each member due to external loads, and K is the member force we got due to unit load at each member. Is the area of each member, and E is Young's modulus of elasticity of material used in each member. So these are the steps that are followed to find the deflection of truss joints. Now I have taken a problem to explain this in a clear way again. So we are going to find the deflection at joint D, where already we have a 50 kilonewton force. So since 50 kilonewton force is acting vertically, so the deflection will be in the vertical direction. So I have to find the deflection, vertical deflection at joint D. So how to find this? First, due to external loads, find out the support reactions. So due to external loads, once we find the support reactions, this is what the support reactions we will get. So support. So you will get these loads. I have not solved the problems here since already you know how to solve. I have explained it in the method of joints clearly. So we are going to find the support reactions. Afterwards, by applying unit load at joint D and removing all the forces, we are going to find the equations of, we are going to apply the equations of equilibrium to find the support reactions. After this, if you see this figure itself, you can analyze that at this joint, the force 2 kilonewton is straight away transferred here. The member in this third force, the force in the third member is equals to 0. If you come to this joint, at this joint you have only two members, where the two members are perpendicular to each other. Therefore, force in these two members are equal to 0. So likewise, if I apply method of joints and find out the force due to external load, then these are the external, these are the member forces due to external loads I will get, that is in the column P. At column K, I have written the member forces we got due to unit load at joint D. since the deflection is required at joint D. L is the member forces, L is the length of the members. So length of the members, all the members are having 3 meter, only the inclined member we have to find. So for the inclined member, the value is 3000 root 2. And last column is A column, that is area column. So if you see this figure, area is given in the bracket and the lengths are here in the blue ink pen. So now this table is ready. After this table, we have to put the final formula of deflection, where deflection at D is equals to summation of PKL by AE. So I'll apply the summation of PKL by AE. So what you can do is you can put another column here where you can get PKL by AE for each member. And for this problem, sorry, I forgot to mention, E is nothing but 200 Newton per mm square. So E, Young's modulus of elasticity of the material, is 200 Newton per mm square. You have to take that value. Only then you will get this final answer. So in the table itself, you'll get some 200 kilonewton per mm square. Kilonewton per mm square. So you will get the final answer, delta D is equals to 34.5 mm. This is about the deflection of trusses. So after this, I'll move on. So to find or to analyze the trusses, indeterminate trusses, which are called as redundant trusses. So these are indeterminate trusses, so in which the very first step is to find degree of indeterminacy. So to find the degree of indeterminacy, we already have the formula. We will put the formula and we'll find it. Afterwards, what happens, whatever the number of degree of redundant we will get, usually we will get hardly 1 for R level. So for the UG level, they will give only 1. So once they give the redundant, we are going to release the redundant, and the member forces in the support reactions under the external load is found, just like the previous case. By treating it as a determinate truss, we are going to find, just the way we did it in deflection of the trusses, we are going to analyze the member forces in each member based on the external loading, releasing the redundant. And afterwards, wherever the redundant is placed, we're going to remove the external force. We're going to put a unit load in the redundant place. And we are going to find the member forces in support reaction, where we are going to get K force system. And then create a table to find X. So as already I have showed you a table. We are going to put another table where we are going to find X, where X is nothing but a parameter which helps us to find the redundancy which helps us to find the redundancy of the truss. So find final member forces by using the formula S is equals to P plus Kx. Now to explain this, it looks so boring. It's like a textbook thing. So I'll explain it in a different way. I have taken some example here. We have a truss here where the truss is having the members. If I calculate 1, 2, 3, 4, 5, 6 members, and the joints are 1, 2, 3, 4 joints. So the degree of indeterminacy for this works out to be 6 minus 4. So yeah, 6 minus 4 into 2 plus 3. 4 into 2 is 8. 6 plus 3 is 9. 9 minus 8 will become 1. So this is degree of indeterminacy we will get. So after finding this indeterminacy, we have to carefully release the redundant, any redundant we want. So one extra redundant is there, we will release this. Sometimes in the problem, they themselves will give which is the redundant force. We have to consider. Since nothing is given in this problem, I'll take BC has a redundant member. Redundant member is nothing but indeterminate member, which we cannot solve by using equation of equilibrium alone. So what I do is I will release this. I will cut and I will release this redundant. I will make in such a way that I'll apply first the external loads and then the redundant. So with that, what I will do is I will mention, or I will call the member forces in the total with redundant. It is called as S1, S2, S3, S4, S5, nothing but S system of forces. I will say it's the final system of forces. To find out which, I have divided the structure into two parts. One the structure without indeterminacy, or I can say a determinate truss with external load. I will analyze this due to external load, and I will call these are P force system. And on the other hand, we have another determinate force, a determinate truss, wherein redundant force is our external load. So by considering redundant force, we are going to find the member forces. Now again, to make it further simpler, what I'll do is I'll take that X outside. Once X is taken, here I'm left with unit load. So once you take unit load, you will get it as a K system. I'll call this as a K system. So the formula is like this. If you want S system of forces, then find out P system, find out K system, and just multiply the product of K with X, and you will get the final forces in the redundant truss. But there is a check, we don't know what is X. So what is X? X is a parameter which we are going to get by using a strain energy principle. So strain energy principle tells that total strain energy in a truss is equals to U is equals to P square L by AE. P here is S system of forces, final P. So I have considered it as SI, that I indicates the each member forces. So SI whole square Li divided by 2AE. This is the basic equation which we got from strain energy is equals to half into load into deflection. So by using the basic equation, we arrived at this equation. Whereas we had S, according to this, S is equals to P plus KX whole square. So I have put that formula here. So afterwards, to analyze this redundant truss, I have to differentiate this, or I can say I have to apply minimum strain energy principle, which tells that dou U by dou X is equals to 0. So if I differentiate this U with respect to X, I will arrive at this formula. But I want X. To find X, I will take X outside, I will send this to this side, and the remaining thing to the denominator, I'll get this final answer. This is the value to find the parameter X. The final redundant truss value we have. So to find X is the formula we know. So now if you see this formula, we have P, K, L, I, A, I, E, I. Again here K, I, L, I, A, I, E, I. Everything is just the same thing as we did it for deflection of trusses. So to analyze that, we have a simple procedure. So step 1 is to find the degree of redundancy or indeterminacy. Remove the redundant member and determine the force in all the members due to external loading and call this as a P system of force. Then remove the external load and apply unit load along the redundant member and determine the member force due to unit load, call that as a K system force. And then you have example, continuing the step 4, find out summation of PKL by AE and summation of K square L by AE by putting the table, by drawing the table where you're finding member forces P, member forces K, and member lengths L, member areas A, and member material Young's modulus of elasticity. All that put together in a table, you will get all these values. After finding that, you are going to put the formula for X and then determine the final forces, final member forces by using this formula. This is how we resolve redundant trusses. Since this is a huge big process and half of it is already taught in the deflection of trusses and method of joints, I'm not doing it in detail. I'm not taking any example. But you should know these concepts of minimum strain energy to tackle it in the gate. Just know the concepts and try to solve it as fast as possible, and be careful while taking the redundant on your own. Moving on to the next concept, arches. Very interesting, very beautiful structure. An arch structure. Arch is said to be an inverted cable structure. It resists load only in compression. You can observe here, if I apply a load at this point like this, this entire arch tries to fall down like this. It will try to fall down. To take care of this, 2 hinges are provided at the abutment. Hinge means hinge is a structure which provides the reaction in 2 directions. So hinge will protect the arch. by falling down in the downward direction, by providing VA and VB has vertical reactions, and it will stop or it will resist the falling down of arch along the horizontal direction by giving a horizontal reaction HA and HB. So as I told you, in the arch section, arches are usually connected by hinges, but this need not to be same in all the time. This can even be a fixed arch. I'll tell you the types of arch later. So here we have considered a three-hinged arch where A, B are the two hinges provided at the abutment. Abutments are nothing but the supports of arch. And at joint C, consider this as joint C, which is nothing but a hinge provided at the crown. Crown is nothing but the highest or peak point in the arch. So you will get this. So this arch resists the load by providing compression. That means it is just pushing this support or abutment towards the center so that whatever the load that comes, it should avoid by resisting through compression. It shows compression. Against the compression force, it shows compressive stress. So now the bending moment coming on the structure will be less when compared to the beams. I will tell you this in the later slides. So whatever the bending moment that comes on this structure will be less when compared to beam for the same type of load. If you apply, say, some 500 kilonewton loads on a on an arch, so whatever the bending moment that is developed will be usually less, will be 100% lesser than whatever that is developed due to the same 500 kilonewton load on the same span beam. Okay, we have certain explanation of the concept for the same. I'll explain it in the later slides. Now it is said to be strong in compression, but also takes bending moment and shear forces to certain extent. So if you cut this section and observe, at each point it will take compression. At the same time, at each point it will take the shear as well as the bending moment. So you will get bending moment at each point and the shear force at each point of the arch. But this is not so prominent in taking bending moment and shear force. It is usually provided at the places where the load coming is compression load, and the structure is very huge that if you provide beam structure, it will affect the economy as well as it will affect the structure in terms of bending moment also. The bending moment is reduced means in turn the cross-sectional area required is also reduced. Now this is about the arch. Now let me see what is the advantage or what is the difference between arches and cables. These are compression members, as I told you, whereas cables are tensile members. So to give an example of a cable, take the chain that we wear, the jewelry chain that we wear, or the ankle chain that we wear. If you take the chain, we can flexibly, we can hold it. We can mold it into any kind of shapes. Okay, it will never take compression force. It will never take any kind of bending moment. Only thing it resists is if you hold the chain on two ends. If you hold the two ends of a chain, what happens if you push it? If you try to compress it, it will not show any kind of resistance. If you try to rotate it, if it will then also it will not show any kind of resistance to bending moment. But at the same time, if you drag it, if you provide a tensile force on either end of the this chain, then it will provide enormous amount of tensile force. So cables resist the structure by tension, and it will never take bending moment, and it can be molded to any kind of shapes based on the loading. The way you apply the load, it will change its configuration, and it has no resistance to bending. Whereas on the other hand, if you see the arch is entirely different. So if cable takes the load by tension, arch will take the load by compression. And arches are rigid members. The shapes cannot be changed with the loadings. It will stay the same. So the compression, even though it is a compression member, as I already told you, it can take the bending moment and shear force to a certain extent. So these are the basic difference between arch and cable. Moving on, arch and beams, if we compare. As I already told you how this happens. I'll take a beam of length L, where the load P is applied exactly at the center. I'll take the same span L of a 3-hinged arch where the load P is applied exactly at the center. So once you see this, the concept is very simple, or we say using common sense, I can say, if the load is applied exactly at the center, the reaction should be half of it. Then only the system is in equilibrium, whether it is an arch, whether it is a beam, the same concept. So if you come to beam or if you come to arch, in both the cases, the reactions are P by 2 and P by 2. If you want moment at any section of X, I'll take first beam. If I want the moment about X from point A, this is from point A about X. So the sign convention we usually use is what? This is any section X. This is not a equation of equilibrium. So we are not considering clockwise moment positive. Remember, that is only for equation of equilibrium. Now I am taking moment about any section X. If it is about any section X, then the sign convention will be sagging moment positive. The moment which creates sagging will be positive. So if this is a section like this is a member. This member, if it sags like this, the moment which causes this member to sag is treated as positive. With that, left side clockwise moment is positive. See, this moment created by RA about point X is moving like this. It is making this member to move or to lay down in a sagging position. So RA into X is the bending moment at X point. So MX is equals to P by 2, which is nothing but RA into X, which is positive. So this is the value we get for moment at any section X for a simply supported beam subjected to concentrated load at its center. On the other hand, if we are taking an arch and the same load P is applied, same reactions are developed. If I want moment at such points, now see what happens here. I'll apply summation fx equal to 0 here, wherein I'll get HA is equals to HB. Of course, I don't want HA value right now. We'll find it later. So if I want moment at this point, here, since there are no vertical forces, no horizontal forces, you don't have horizontal reaction, but this is not the case. So wherein this vertical force, even though it is vertical, it will try to make this body to move towards left and here towards right. So to resist, HA and HB will be developed. So if you want moment at this section X, MX is equals to, so now see this is creating a sagging moment. Left side clockwise positive, left side clockwise, that is P by 2 into X, the first value. Another value at this section X, no, we are not taking here, we are taking here, remember. Section X is here, now HA is moving like this in the anti-clockwise direction. Left side of the section anti-clockwise is negative, so minus HA into the distance, I'll call this as Y, HA into Y. So when you need an arch moment, if you see this P by 2x, it is a beam moment. Arch moment is always lesser than beam moment. See, P by 2 is a beam moment. Beam moment minus HY. HY is called as a hogging moment of an arch created by horizontal thrust. So this hogging moment of arch tries to reduce the moment coming on the structure. So that's the major advantage of using arch over beams. Since the bending moment here is less, the cross-sectional area required will be less. Thus, arches are provided wherever you have a larger span where beam should be provided. Now, advantages, if you say, arch has less bending moment when compared to beam that we saw. For the same bending moment or for the same external loading condition, cross-section of the arch required is less than that of beam. Why? I have showed you now. The disadvantage here is to construct an arch, you need a skilled labor. Without a skilled labor or skilled supervision, we cannot build a beautiful arch to resist the compression force. So afterwards, we are moving on to the types of arches. there are three main types of arches. I don't say these are the only type of arches that is available. I have considered only three main types of arches, among which one is two-hinged arch, where the hinges are provided only at the abutments. And then we have a three-hinged arch, where the hinges are provided at the abutment and the crown point. And the last one is a fixed arch, where the abutments are provided with fixed supports. These are the three different types of arch, among which if I take two-hinged arch, it is an arch with four unknown reactions minus available equations of equilibrium for two-dimensional system is still 3. So 4 minus 3 is 1. So two-hinged arch is an indeterminate structure. On the other hand, if I come to three-hinged arch, it has four unknown forces, unknown reactions. 4 minus 3 available equations of equilibrium will get one more indeterminate reaction, which we can find by one more equation at this hinge. We know that at hinge, the bending moment will be equal to 0. So if I put MC is equals to 0, I'll get forces in all the four reactions. Hence, the three-hinged arch is a determinate structure. If I go to fixed arch, there are 6 number of equations. So to 6 number of equations, we have 3 equations of equilibrium. 6 minus 3 is 3, hence we have indeterminacy, degree of indeterminacy is equals to 3 for a fixed arch. Now I'm taking the analysis of a three-hinged arch, where a few things that we should know is a three-hinged arch, as I already told you, is a statically determinate structure having the hinges at the abutments and the crown point. There are 4 unknown forces, which we will be finding through 3 equations of equilibrium plus 1 additional condition of moment at the crown. So all 4 I have written here with the sign convention. You can observe the sign convention. These 3 are equations of equilibrium. Especially look into this moment. Clockwise moment is positive for this case, where MC is the moment at any section. If you take moment at any section X or C or anywhere in between the beam, if you want moment, not the algebraic sum of moment, just the moment, then this is the sign convention that we should use. Now, y is the height of the point anywhere in the arch. If you want, you can put this formula. So I have given you the formula to remember. Y is equals to 4hx divided by L square into L minus x. This is the three-hinged parabolic arch formula. So this formula is right away, we can take it from the mathematics, or even in civil engineering, we have a separate derivation to derive this formula. Let's see what is the procedure to analyze this arch. So we have around 4 steps. In the very first steps, we are finding the unknown support reactions. In the second step, we are finding at any section X, we are finding the moment, for which we are putting the formula y is equals to 4hx divided by L square minus L minus into L minus x. And if you want the slope of this arch at any section, then you can go with the tan theta is equals to differentiation of the y equation, that is dy by dx. And if you need a normal thrust, if you cut the section at any point x, then you will get a normal thrust, a normal reaction, I can say, and a radial shear. Both we will get normal thrust and radial shear, and we have a separate formula for that. Of course, we have a derivation for that. But for the gate concept, we just remember the formula. Nx is equals to Vx sine theta plus h cos theta. And Rx, that is radial shear, is nothing but Vx cos theta minus h sine theta. You have to remember these 2 formula to tackle only these 5 steps we are following to analyze the arch. Only these 5 steps. Now moving on, I'll take a problem now. Analyze a three-hinged arch subjected to UDL throughout the span. See, I'm giving you the concept. I'm solving this problem in detail, but in some papers of GATE, they have asked what is the reactions at section X or at joint A, and so many questions on this topic. So I'll take an arch subjected to UDL throughout the span. If that is the case, as I already told you, if the load is P at the center, the reaction will be P by 2, P by 2. It's a common sense. At the same time, if the load is W spread over throughout the span L, then the total load will be WL. The reactions will be WL by 2 and WL by 2. We have to find HA and HB. We will find it by applying equation of equilibrium. So VB, VA. So if I put summation Fy, VA plus VB is equals to minus WL, we'll get this. VB is equals to WL by 2, VA is equals to WL by 2. By applying the moment equation, we will get. Afterwards, to find H, I'll apply sigma Fx first. Plus HA minus HB equal to 0. There are no horizontal forces, hence it will not fetch you the value of HA. Instead, they will say that the horizontal reactions or horizontal thrust are equal. Then afterwards, I'll put MC equal to 0. That is moment at crown point is equals to 0. And the sign convention we are using is this. I'll consider the left-hand side. In the left-hand side, VA into distance is L by 2 minus this is HA into the distance is H. And then you have a UDL here. UDL of W spread over L by 2. So W into L by 2 and the perpendicular distance of this half of portion is L by 4. So this is the equation we'll get. With that H equals, we will get is WL square by 8H. You can remember this formula or you can solve it. So HA is equals to WL square by 8H. So now moving on. This is the major and important question usually asked, that is moment at any section X. If you want moment at any section X, I'll consider we need to find what is Y first. We know that Y formula is 4HX divided by L square into L minus X. If I want moment at any section X, this is VA into X minus HA into Y plus W into distance is X. I have to consider W into X into X by 2 is WX square by 2. So the formula is ready. We will put, and if we just simplify, we will get moment at any section X is equals to 0, which tells you that if a 3-hinged heart is subjected to UDL throughout the span, then moment at any section of this arch will be equal to 0. Now moving on to second problem. We have another problem. See, this problem I have solved in detail just for your knowledge, and I hope this type of big problems are not asked in the gate, but tricky simple problems with the concept that is available for the entire problem, whatever I'm teaching will be there. So I'm solving only one problem in a complete stretch. So there is a hinge subjected to so much of load, and they want us to find the bending moment, normal thrust, and radial shear at a distance 5 meters from support A. So the first thing is we are applying equations of equilibrium for the whole structure along with the bending moment at point C is equals to 0. We will apply that and we will find what is the reactions. So that is what we do first. So we are applying the load. We are putting MA is equals to 0, we got VB. We are putting sigma Fy equal to 0, we will get VA. And applying MC is equals to 0, we will get H. And we have to find the reaction, since in the question they asked us to find the reaction at the support. Once they ask just the reaction, then we have to find the resultant reaction at the each support. So that we have found here. Moving on, Y at a distance 5 meters is found by 4HX by L square into L minus X formula. We have put that formula and we arrived at the value of 3.75. Bending moment at 5 meters, that is MX formula, we are going to put. Have considered left hand side, wherein VA is moving in the clockwise direction, so plus VA into 5. And H is moving in the anti-clockwise direction, so minus H into 3.75. And we have only one load to the left-hand side, minus 20 into 2. So with that, MX, M at, that is bending moment at section 5 meter from left support A is minus 115 kilonewton meter. To find the normal thrust, I will cut the section and I will enlarge that section. This is what we will get. At this joint, we'll have a vertical reaction. We have to find that vertical reaction, which is nothing but Vx. We need it. And we need angle theta. Okay. To know angle theta, I will take this y, basic y formula, parabolic rise formula y, and then I will differentiate it once. With that, I'll get the slope value. Okay, x I have kept it as 4hx by L square into L minus x. So if you differentiate this, 4h by L square is a constant, I'll take it outside. The remaining thing is Lx. Differentiating Lx, I'll get L, and then minus x square I'll get. So differentiating x square, I'll get 2x. So this is tan theta value. So substituting the values and finding the answer, theta will be equal to 26.56 degree. Afterwards, we need Vx to find Nx. So Vx, we are applying simple equation of equilibrium of summation Fy equal to 0. So we'll get plus Va plus Vx minus 20 equal to 0. No other vertical forces. Plus Va plus Vx minus 20 equal to 0. With that, Vx is equals to 79 kilonewton. And then now Vx is ready, theta is ready. Now we have to find what is the normal thrust. So normal thrust is Vx into sine theta plus h into cos theta. Vx into sine theta plus h into cos theta. 79 sine 26.56 plus 152 cos 26.56. With that, we will get normal thrust as 171.28 kilonewton. And we need the radial shear. Radial shear formula is Vx cos theta minus h sine theta. So radial shear, if we put the value, we will get this final answer of 2.69 kilonewton radial shear acting at a distance 5 meter from left support. This is how we solve the problem of a three-hinged arch in detail. But the question asked, problem 2.3, the question asked in the GATE exam will be something like this. An isolated load W is acting at a distance A from left support of a three-hinged parabolic arch of span 2L and rise H, hinged at the crown and the abutments. Once they say hinged at the crown and abutment, it's a three-hinged arch. The vertical reaction at the support is. So we have to check this clearly. They said there is a force or a load W is acting at a distance A. It is something like an eccentric loading acting on a three-hinged arch, three-hinged parabolic arch, the span of which is 2 times the L and the rise is H. So if you can write it, kindly write the diagram and check it how it will work. So at a section A, I want at section A, there is a load W. I want the reaction, vertical reaction. They didn't say which support, either A or B support. So what I'll do is I'll take right hand support. So I will consider sigma MA equal to 0, or I can say summation of all the moments about the left hand support equal to 0. If you put that, you will get the force, if I consider it as RB in the right side, RB into the distance 2L minus W into distance A. With that, RB is equals to WA by L. This is the value we get. WA by 2L, sorry. WA by 2L. So the answer is A. In this problem, answer is A. And then moving on to the next problem, an isolated load W is acting at a distance A from the left support of a three-hinged parabolic arch of span 2L. Yeah, I have completed this. Now I have to go to this. If three-hinged parabolic arch of span L rise H is carrying a uniformly distributed load W per length over the entire span, then which of the following is true? The same thing, we have solved this problem by considering three-hinged arch subjected to UDL throughout the span. So if that is the case, we know that horizontal thrust we got is WL squared by 8H. So A is correct. We know that bending moment at any section mx is 0. That is also correct. If you want to know what is the shear force at each section, then you have to find radial thrust at each section. So if you find the radial thrust at each section of a three-hinged parabolic arch subjected to UDL throughout the span, then shear force will also be equal to 0. This is another important thing you should note. So if three-hinged parabolic arch of span L rise H carrying a uniformly distributed load W over a length, over W per meter length over the entire span, then its horizontal thrust is WL squared by 8H. The shear force will be 0. The bending moment will be 0 at each section of the beam. Sorry, each section of the arch. With that, before summarizing, we have a few questions. Okay. The question here is, if a force is compressive, should it be away from the instead of or towards the joint? So I didn't get the question correctly, but as per my knowledge, I'll try to answer it. So if the force is compressive, it should be towards the joint. It should always be towards the joint. Why is this? If you want me to tell why is this? Okay. Is the slides are visible? Yes. If you want me to show how is this possible, I will take a pointer option. So if this is the load, or I say if this is a member, see this has a two joints. If it is a compressive force, what usually applies, what usually done in the joints is the loads are applied externally from outside to inside like this. This is how the loads will be applied. See, the compressive and tensile force, what we are talking in the trusses are internal resisting forces. That's why we find degree of internal indeterminacy. So we have to find the resistance. If the loads are coming from outside to inside, then the member will resist from inside to outside like this, inside to outside. So this is a compressive force resistance. This is a compressive force. So that's why we write the force towards the joint has compressive force. The force moving towards the joint has a compressive force. This is the reason to do that. Okay. And then what is this? In problem 1.2, I'll go to problem 1.2. Okay. Hope it is cleared. Now let me go to this again, truss problem 1.2. Yeah, we are on 1.2. Yes, we are on 1.2. Yes, the question asked is, isn't it 100 has external force of 100 is applied? No. Okay, I'll come to this problem now. Again, to whoever friend asked, now I will explain you again. This is a zero member concept. Okay. If you take joint D here, if you take joint D, you have 1, 2, 3, 4 unknown members and one known force 100 kilonewton. So if you want to start from joint D, then you have to consider a free body diagram with 5 forces. The other option to find the member force in DE is take joint E. If you take joint E, at joint E, you have 3 forces, AB and AB, BE, sorry, AE, BE, and DE. So for example, if I have calculated some value at joint A, say for instance, it is a compressive force like this type of compressive force we got, say it is about 5 kilonewton. I'll write 5 kilonewton here. So what happens at this joint? If I apply sigma fx equal to 0, then what will happen? This is minus AE, since this, okay, plus AE right side. And this is also plus EB. So EB will become minus 5 kilonewton. So your answer is like this. Again, this is also compression. This is 5 kilonewton. Since these are collinear. And the third member, if you put sigma Fy equal to 0, this will become 0. That's why force in member DE is 0. What is this? Isn't EL 0 as well? I don't know for which problem they have told you. Just a minute, let me read the question again. Sorry, I didn't got the question. Isn't EL 0 as well? I'll move on to other question. For zero force member, does case 1 apply if B was a hinge or roller? For zero force member, does case 1 apply if B was a hinge? So I'll go to this again. So all the questions are from trusses only. So this is case 1. If B was a hinge or a roller, no. Yeah, this is the case 1 of zero force member. No, if there is a roller or a hinge at this support, what happens means you will get another force here, which tells you that the joint B is having 4 forces. If that is the case, then now this member is not equal to 0. BD is not equal to 0 if that is the case. It can happen only when only 3 forces are there and 2 are collinear to each other, then only the third member is 0. Okay. Someone asked to find, please explain external degree of indeterminacy. The external degree of indeterminacy is very simple. You might have studied it in engineering mechanics in the very first year in the physics cycle itself. It is simple. Find out the support reactions. I'll tell you this problem only I'll explain. See, for this, here we have a hinge support. At hinge support, we have 2 forces. At roller support, we have 1 forces. So total external unknown forces available. See, these are member forces. Member forces are internal forces always. As once this load is applied, first it is tackled by the supports, then by the members. So if you take this support, these supports will also take the load of this entire truss. So to resist this, the reaction should be something like if there should be certain amount of support reactions. If these reactions are found by equations of equilibrium alone, then it is again a determinate structure. Degree of indeterminacy is 0. So if we take the whole structure, equations of equilibrium available are only 3 again, sigma fx equal to 0, sigma fy equal to 0, and sigma mz equal to 0. If you have only 3 equations of equilibrium, and if you have only 3 unknown forces, all 3 unknown forces can be solved by 3 equations of equilibrium. Then the degree of indeterminacy will be equal to 0. So I will take that problem. I'll go back. Yeah, you can see here, this is a hinge where we have 2 unknown forces. This is a roller where we have 1 unknown force, totally 3 unknown force, 3 unknown force minus 3 equations of equilibrium. So external indeterminacy is 0. So this is how we solve degree of external indeterminacy. I hope that's it. But DE and 100 kilonewton are collinear. Okay, Guru Kirtik, whoever, I'll go to that problem again, Guru. See, Mr. Guru, kindly look into this joint B here. I'll tell you, if you want to apply the zero force concept, zero member force concept, then the basic condition is the joint should have only 3 members, or it should have only 2 members, no other forces. So if that is the case, okay, if that is the case, see now, only 3 members are there here. Hence, 2 are collinear, then the third one is 0. Simple, you apply sigma f, y equal to 0, you don't have any other component except this BD sine theta. So BD sine theta equal to 0, nothing but BD is equal to 0. Very simple. On the same line, if you take the joint, where I left that joint. Okay, I'll go to that problem. I'll show you again. Yeah, see this. At joint D, you have 5 forces. You cannot apply. But at joint, you have only 3 forces, out of which 2 are collinear. Hence, if I take sigma Fy equal to 0, here, force in member D is equals to 0 directly. Apply equations of equilibrium only, then also you'll get 0 at this joint. Okay. With that, I'll go to summary. summarize, I hope I have I have answered all the questions. Now, to summarize this, we have spoke about the trusses and the 4 different important methods of analyzing a truss: method of joints, method of sections, redundant trusses, and the deflection of truss joints. And then we found the arches, and we have solved 3-hinged arch. Again, we have a semicircle arch left, and 2-hinged arch also, we left it. So I have covered only this much of part. I tried to satisfy as much as possible to myself. And see this, we have completed all these topics. And while tackling the problems in arch, remember, understand the concept, apply it to the problem, and read the problem twice, and then start solving. Okay, with that, I'll end the session, and I thank all the organizing committee members and the coordinator and our HOD for giving me an opportunity to teach you people whatever the small little bit knowledge I have. I shared with you people. Hope you understood. Thank you. Thank you very much. I'll hand over the session to Madhushri ma'am. Thank you.
Thank you, Professor Kanmani, for your explanations and clearing all the queries from the participants. And we hope we have cleared all the topics, whatever the queries and everything, whatever the participants have asked. So we'll meet again on day 4 for the sessions on construction management by Professor Abhilash, and also concrete structures by Professor Arjun. So thank you all for your participation for today's session. See you all tomorrow for your active participation for all the sessions. See you all tomorrow. Thank you.